in testing, right, we use a hammer to excite a 1 degree of freedom system with an impact. That impact is an impulse, same thing in this sense. However, the hammer accidentally impacts the system twice, right? So our first impact is 0.2 newtons. Let's just call that at t equals 0. And then our second impact is 0.1 newtons at t equals 0.1 seconds. Right, so 100 milliseconds later. So let's plot the response to this double impact. Right, so just kind of some other terms. Let's go with m equals 1 kilogram, c equals 0.5 kilograms per second, and k equals 4 newtons per meter. So we can write a whole equation for this. And you can use this method for 3, 4, 5 impacts, but let's just go with 2. That's enough writing. We can code the rest as f of t. So our forcing function, actually let's just call it that, our forcing function is f of t is equal to 0.2. What Greek symbol are we going to use here? Is this a step function or an impulse function? Yeah, so delta, yeah. Don't confuse me like that. I will write sigma and then, okay, so delta, let me write a cleaner delta. Delta of t plus 0.1 delta of t minus tau. Right, so tau is the offset between our first and second impacts. So consider that the unit impulse has a magnitude of 1. We can obtain the same solution that we did for our general impulse. And we have this, but I'll walk through it, right? So we have our equation of motion, which is mx double dot. I guess that should be of t, right? Because that's how we're doing it in this chapter, to not be confusing. Mx double dot t plus cx dot plus kx is equal to 0.2 delta as a function of t. Take the Laplace of both sides and ignore the initial conditions. Okay, so let's take the Laplace of both sides. We're going to have m times s squared x of s. I'm going to ignore my initial conditions, so I just drop what's left there, plus c. I'm going to drop the parentheses too, I don't really need it. C s capital X of s plus k capital X of S is equal to 0.2. So if I go ahead and pull out X of S, divide by divide through by our terms, we're going to end up with X of S is equal to 0.2 over M times 1 over S squared plus 2 zeta omega n S plus omega n squared. Again, we can use number 10 in the table to kind of pull us back out, take our inverse transform with number 10 in our Laplace table. And this is going to give us just what we had before, which is X of t is equal to 0.2 over M omega d e to the negative zeta omega n t sine of omega d t. Right, so the only difference here is that before we had 1 over m omega d, and now we have 0.2, right? And you didn't have to walk through all those steps. You could have seen that, but I think it's helpful to kind of show you that you can if you want, if you want to back some stuff up. So, however, let's go ahead and call that x of 1 of t, because we have to solve this again, right, for x of 2. And now we have our offset tau. So x of 2 of t is just going to be x2 of t is equal to 0.1. We don't need to solve that again, right? M omega d e to the negative zeta omega n of t minus tau sine of omega d of t minus tau. Right? So these are our two equations, which we can go ahead and solve for. Which are actually pretty easy. I mean, we don't have to solve for, right? We can just go ahead and plot, and then we can add them to each other. Because we know that the system are linear, and the Laplace transform of a linear combination of two transforms is the same as the linear transformation of these functions, right? So we can build this into a piecewise function. Because they are linear, we get a piecewise function which looks like this. X of t is equal to, for our first impact, right, it's just going to be x of 1. So we have 0.2 over m omega d e to the negative zeta omega n t sine of omega d t, and that's if t is less than tau, and our tau is 100 milliseconds here, but we'll write it out. And then our second one, because I have a minute left of class, I'm just going to copy this. I want to get our plot in. So it's the exact same term, right? But because they're linear, we can add 0.1 over m omega d e to the negative zeta omega n t minus tau sine of omega d of t minus tau with a bigger parentheses, right? So that's if t, if tau is less than or equal to t. And so this plot it's going to look like this, right? So we have our first impact, which is the blue line here, and we have our second impact, which is the orange dashed line, the blue dotted and orange dashed, and then our total response is just a summation of the two, right? And you can see that we have a, my pen died. So you can see that we have an offset here, right, of about 0.1 seconds.